9 hours. It did help that I had the labeling for you.
Yeah.
So you had 23 items, right, everybody?
We did.
149. Communalities, hopefully, again, communalities can be a wonderful way to start to see, and hopefully you all looked at your communalities. Again, no hard and fast rule. My own thinking is, I like them more than 50%. The book says average 60. So you look for ones that are particularly low. Like, did anyone see that one of them had 45% when we use the Varimax rotation? Varimax is what? Orthogonal or oblique rotation? Orthogonal. What does orthogonal rotation mean again?
Correlation.
Yeah, uncorrelated. And so that's why the initial communalities are 1.0 for principal components, because principal components puts 1 on the diagonals, which means principal components analyzes what, everybody? All the variance, right? It maximizes variance. What does H square mean, everybody?
Commonality.
Yes, and U square?
Unique.
And uniqueness is a function also of what? Error.
Yes.
What does the S stand for? Specific variance.
Specific.
Right, specific. So most of the items look pretty good. You know, there's a few low ones. I do see a 41% for I wish I was in better health.
Yeah.
And 46, you know, which isn't horrible, but it's not great. So that's a really nice index, potentially, of seeing how we're doing. Some people use the Kaiser-Meyer-Oken measure sampling adequacy, which means you have sufficient sample size, 0.822. I don't use it that much. And now as we scroll down, everybody, did anyone get about a 5-factor solution?
I got 6.
6.
You guys, okay, I'm sorry, 6, yes. 6-factor solution. How many did we expect? Given that I already had the labels.
6.
Yeah, because I had the labels.
So what if we went down to a 4 and did it at 54.9%? Is that a
You mean
bad
you
thing?
restricted it to 4?
Restricted to
It's
4.
not. It's just saying I think it's 4-factor. Then you got to try to make sense of that 4-factor, and that's a big chunk. That's a huge difference in variance explained. Okay. So that probably tells me a 4-factor isn't great, but I'll do that sometimes. Say if it looks like they're what we call trailing eigenvalues, small eigenvalues,
Yeah.
I may try to see if a 4-factor, once again, decrements the instrument that much. Now, that's when I use the maximum likelihood. The maximum likelihood option is extraction because you can get a chi-square test. Here, 65%, which is real typical. We get 6 eigenvalues, and then the unrotated, we see 29%, 11 for 2 of them. Then, as you know, when you rotate it, the variation starts getting more equally dispersed. The component matrix, as you know, is critical for being able to compute the factor loadings, but it's pretty uninterpretable per se. The rotated component matrix. So, the first one, it looks like we have items such as psych well-being, but did anyone notice psych well-being and social support loaded on the first construct?
Yes.
Now, if I didn't give you those names, you would have been maybe a little bit already biased by how you're going to name them. So hopefully you came up with your own.
Well, especially in the 4-factor, they both loaded on the same one, which is why I eliminated the social support.
Right. And I would still, hopefully you still did the analysis, the full analysis with all 6 factors, did your interpretation, and then use the 4-factor as a second model. I wouldn't want you to go straight to a 4-factor because you don't have a theoretical basis for
No,
that.
well, I did do I ran it both ways. I ran the 4
Yeah.
and 6, but when I decided to go with 4-factor model, most of my interpretation is on the 4-factor model.
Oh, okay. And then
Did I just do that backwards? I should have
Because
started at 6.
especially with the principal axis factor, it wouldn't even converge with less than 4 factors.
unless you maybe got rid of some of the items, some of the offending items.
Yeah, but without getting rid of the items.
No, I wouldn't have a problem. As long as you interpret initially the 6-factor solution, right? As long as you interpreted initially the 6-factor, then it said, however, there's a couple of, let's look at the 5th and 6th. The 5th and 6th. I see one for I do not have enough time to exercise. And not much here, is there? There's some cross-loadings here for the 6th one. I feel that life is overwhelming. Here's, I feel I do not have enough time to do the things I want to do. That kind of gets at feeling, that 6-factor almost makes sense. Right? It's like an overwhelming, isn't it? Kind of a feeling pressure type of construct. So hopefully you did this, interpreted the sixth one, and then I'd have no problem with you trying a more restricted four-factor solution. So the big thing is, did this six-factor solution come out the way we kind of thought it would? Did it come out? No, right? Because then all these items, right? Cyclobean would be there. Look at cyclobean. I have an item there. I have an item way over here. I have an item there. I mean, cyclobean, this one, did anyone notice that this one kind of cross-loads, the fourth one?
Yeah.
Or it's kind of low. So that's where you want to make sense of it. Now, this is real data, so you can see that things aren't always very clean, right? This is real data. I did not make it up.
Where did it come from?
It came from actually a project done in San Diego State. A project done in San Diego State. So then you would just make sense. Now, you said when you ran principal access factoring, it did not converge. Is that true?
Yeah, we're in, not even with multiple. I increased to like 75 iterations and it still would have converged.
Okay, so here we see.
I increased it to 100.
I went to 100. Yeah.
And it did, right? So, extract. So when you just increase it to 100, nope, I can tell. And how I can tell right away that it didn't converge, I can look right here, even right there, and see it doesn't give me a rotated thing in the listing. Yeah, so if beyond 100, you can always do it to 200. But here you can see there's some problems with it. Did your oblique, your oblique rotation converge with PC?
PC.
Yeah, PC it did. Yeah. Did the oblique rotation tell a very different story on the six-factor solution, or was it pretty similar?
Pretty similar.
Yeah.
I
You
thought
got it.
some of the loadings switched around on that.
It does switch. Yeah, you will sometimes find an
That was-
oblique rotation will do that.
But so I obviously missed class, but I saw the switches, like the switching on the loadings, and talked about how it might be like a less stable loading, which is why I discussed the four-factor model
Got it. Now,
after doing the full interpretation.
one thing I want to show you, Chad. So let's say we used maximum likelihood right there, okay?
Okay.
So let's use maximum likelihood and so there's maximum likelihood. We'll use principal components. We get a six-factor solution. 54%. It's a bit lower of maximum likelihood. There's the factor matrix. And then we get a goodness of fit test. You can see right that there is significance, which indicates that actually the model doesn't fit well, because you want the model to fit the data. So here, do you see that 178.21? 178.21. Now let's run this. Let's run this with a four-factor solution. Okay? So now I go ahead and constrain it, or I restrict it to a four-factor solution. 47% is counted for. So it's going to be less. It's going to be less. I'd be really surprised that your six-factor solution is going to be the same, because it's a more restricted, it's a more constrained solution. So here we have a four-factor, and then you want to see, looking at the rotated factor matrix, if it makes sense. And did you think it made more sense, Chad, when you interpreted the four-factor?
Yes.
Okay, because I've seen items here. The environment, a couple of the environment items load there. Let's see if we still get psych well-being. There's all the social support items. Psych well-being still kind of goes with it, doesn't it? The psych well-being and social support. Why? Did anyone delve into that? We thought, when we created this instrument, they thought psych well-being, I have a positive outlook, I feel life is overwhelming, I'm usually able to adapt to changes. Kind of, some of this went with, I have no problem with people to turn to, I feel as though I have a good support system, I have one special person. Do those seem like maybe they kind of...
Yeah, I said it was more like an overall measure of satisfaction with life.
Okay.
Because all those components are kind of integral to assessing.
Okay, and that's the type of thinking you want to go through when you name this latent construct. So Chad, then, if you did the 6-factor, did that, then the 4-factor, that'd be no problem. Now look here. Here's your goodness of, where's my...
I didn't see it as you scroll down.
Okay. Factor transformation. One or more commonalities greater than one were encountered during iterations. That shouldn't happen. Okay, so here, when you constrained it, interesting, I didn't get the goodness of fit. So I got goodness of fit there. 178, it doesn't have a good model fit. I constrain it to 4 factors. The determinant, so it doesn't like it. I'm not even able to compare. One or more commonalities greater than what? It doesn't like the 4-factor solution. Can't, because you know what it means to have a commonality greater than 1? What does that mean? This will be helpful if you ever get knee-deep in a structure equation modeling. What does it mean to have a commonality greater than 1.0? Here, I'll make life a little bit easier for you.
There's an
You're
overlap.
exploiting more variance.
Yeah.
Should be able to explain.
Hey, R squared goes from what?
0 to 1.
Yeah. Wow. Ross writes up in his dissertation, I got incredible R squared. I explained 132% of the variance. Should Ross be really happy and we all pat him on the back, or say, Ross, maybe you should go back to the drawing board? Do you see that commonality as greater than, so for your 4-factor solution, you got a problem here. This is called a Haywood case. This is technically called, and there's a body of literature, it's called a Haywood case. When you have negative variances, R squared is greater than 1.0. And you'll get that screwy stuff in structure equation modeling. You will get Haywood cases. It's inevitable. So all of a sudden you're going to get an R square of negative 0.32, or Ross's 1.32, and then Zach's going to get a variance of negative 0.32. Wow, that's amazing. He has defied the history of mathematics by having a square number be a negative. And we're not talking about the notion of what's called complex numbers, which is, which does have that whole area. That's the screwy stuff that happens with your 4-factor solution. So you can kind of get the output, you get the printout, but there's a chance you got that little error message that you may or may not have acknowledged.
I don't remember seeing.
Did you use PC when you did your 4-factor? Okay, it may have been okay with PC.
Okay.
With maximum likelihood, it wasn't.
I did not use maximum likelihood.
Okay, so let's just do PC then, with your 4-factor solution. I bet you don't get the error message then. Nope, you don't get the error message. Yep, you're okay. 54%, no error message. A maximum likelihood you did. And maximum likelihood is very close to what's used in structure equation modeling, which means there's still, in other words, I would still probably have some concern about your 4-factor solution. But you do see, right, a lot of the items, did you find, Chad, that a lot of your items from psych well-being and social support loaded on one construct? And then this 4th one, okay, the environmental items.
Mm-hmm.
Environmental items.
Environmental and spiritual only loaded themselves, but there was some overlap in columns 1 and 3.
So I would look at that 6-factor solution first, the initial, just unrestricted, then the more restricted model. Now I am concerned that when I use maximum likelihood, we had commonalities, we had Haywood cases. So I am a little concerned about that. Which means if you try to fit the 4-factor and confirmatory factor analysis, I bet you it wouldn't fit so hot. I bet you it would not fit so hot.
I kind of made a case for 4 factors because despite the lack of convergence with PAF, but also just the eigenvalues, how those last 2 eigenvalues were barely above 1.
Okay.
There's that kind of trail off.
Uh-huh.
It went from like 1.5 to like 1 point close to 0.
Okay, so that was...
And then, because you said the Kaiser criterion isn't like a strict cutoff, right? So...
Yeah.
So that the fact that those kind of trail off so sharply, like I always thought that sharp drop off was a reason to not use those values.
And also then, again, I don't get too strict on these cutoffs. Because what if the Kaiser criterion was 0.99 and the items looked pretty good? It made sense. What if those two great items that got up being overwhelmed? So I would also use your judgment and interpretation also. I mean, these cutoffs are helpful, but absolutely. But I think you guys are really in the right way of thinking about this. I think you approached it the right way of thinking about this. Do you see, just for this little homework assignment where I already had the names for you, it can get pretty complex with that, and it doesn't always come out the way you think it does. It's not always very clean. And I have no explanation why, and I've done hundreds of these for clients, why it's always between about 50 to 60% variance. I rarely get 80 or 90.
There must be some theory in
there must be something out there. I always get about 50 to 60% for the total solution. Always, 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 always. But as you know, PAF will always be smaller, right? Because PAF only analyzes what? Yes, excellent. Excellent. It only analyzes the common factor variance. Okay, you guys. So that is going to be your last homework, I decided. That's it.
Oh, you're so kind.
Can I run the camera until she gets here so that we don't miss the first part of the lecture?
The camera is supposedly
Is
ready.
it on?
Yeah, it should be. I put my little thing on. Yeah. He said it's on. Because I have this. Once I turn this on.
I think he said we had to turn that on.
Yeah.
Oh, good. Okay, good.
Yeah, no, you're being documented. Why, were you thinking you could get away with more stuff not being documented?
I'm always trying to get away with stuff not documented.
Okay, guys. Let's go ahead and finish up a canonical correlation. You've already had tons of repeated measures analysis. You're all experts at it. But I'll still go over some repeated measures. You will not have this on your take-home because you had enough of repeated measures on the in 6022, 6021. But it's always still not a bad idea to go over that. It's such a frequent design. So let's go over canonical correlation, which we left off. Let me go ahead and find. God bless you.
Thank you.
Again, canonical correlation is used for what purpose, everybody? When you have what? What type of presenting problem would evoke the use of canonical correlation?
To reduce dimensionality.
Yeah.
When you have two sets of variables. When you have two, I don't want to waste too much more film. When you have two sets of variables, and you want to reduce the dimensionality. So as I said, some people think it's kind of an obsolete technique. I disagree, and as I told you, I was able to use it in a journal article a couple of years ago with Sharp Healthcare, when they had all these evidence-based practice variables, all these demographics, and we saw which ones kind of went together. So it's when you have two sets of variables and you want to reduce the dimensionality. So it's a close cousin of multivariate regression, right? When you have a set of predictors and a set of criterion. But that doesn't reduce the dimensionality. It just sees how well each one predicts the other. So here, let's use an example, everybody. You will not be doing canonical for the take-home. As you know, there's not a point and click for canonical, but I did show you last week that there is a macro that you can get from SPSS that comes with the package that you can use. So let's just make this the simplest case, which you would really not use canonical correlation for this. But it's just easier for me to show you. As I found out last week, you all were big fans of Sesame Street. Zach even said that he still has a big picture of Big Bird on his wall.
Grover.
Grover. Who?
Grover.
Oh, Grover. Okay, whatever. So, anyway, we have two pre-tests and two post-tests. A pre-test on letters and forms and a post-test. So this is an unusual example to do a canonical correlation, but it's good enough. These are both quantitative variables. And as you know, you need to bring up the macro. Two lines of code. So you save the macro, and I believe I've already saved the macro for you on the notes if you want to play around with it. And then you go ahead and just like any macro, you put it in a subdirectory, and then code is cancore set1. You just type in the name of the variables in the first set. Set2, the name of the variables. That's it. 2 lines of code. That's it. Easy schmeezy. So, as for sample size, some say you should have 20 people to 40 per variable. They like bigger sample sizes for canonical correlation, but once again, it can be done with smaller sample sizes. So look at the output. You get the correlations for set 1, right, which is the pre-test on letters, pre-test on forms. And then you get the correlations for set 2, right? So those are just the correlations within each set of the variables. And here, just to show you, I confirmed it right there. If I ran a correlation on those, there's the 0.506 for the pre's, and for the posts, there's the 0.655. So it confirms exactly that. So there's nothing arcane about that. Now this is when things get a little bit new here. You get the correlations between the sets. You get correlations between the sets. So post-test and pre-let is 0.55. Post-test and pre-test letters, 0.55. So same here. Everything's from the correlation matrix. Everything so far is from the correlation matrix. And now you get canonical correlations. Now you get the canonical correlations, and we have 2 sets for each pair of correlations. Do you see one seems to be quite a bit bigger than the other? So these are the canonical correlations, and you get a test that all canonical correlations are 0, which is the null. So the second one is used to test the linear combination. So look at that chi-square of 21.193, everybody. If you're at all interested in the math, just for funsies, here's the math. You just take sample size, minus 1.5. Lord knows how they come up with 1.5. Some person found that as a constant. Minus P plus Q. P is the number of variables in set 1. Q is the number of variables in set 2, divided by 1/2, times, once again, the logarithm of 1 minus 0.293, which is the R squared, which is right there, 0.293, 21.193. So this basically contests the significance of the variant. But this is when you start interpreting it. This is when you can start making sense. So let's just look at the standardized coefficients. Does everybody see you have a standardized coefficients for set 1 and a standardized for set 2? Does everybody see that? So here, do you see the bigger one for the first variant is 0.669, and for the second one, it's 0.834, which means the pre-test on forms goes with the post-test on letters. That's your first function. That's your first canonical correlation. The second one then, do you see the larger one is 1.056 for letters, and the larger one is post-test on forms, which means the second one, the pre-test on letters and the post-test on forms, that's the variant. That's the canonical variant. So that's how you interpret it, everybody. That's how you interpret to see which of these go together across these sets. Across these sets. So again, pre-test on forms, post-test on letters. So then you have to kind of make sense of why it would go together. That'd be up to the educator who works with Sesame Street. And then you get the raw functions also. You also get the raw functions. As you can see here, this is the higher one. And for pre-test on forms. And these are really close. Post-test on letters. Here we see pre-test on forms, post-test on forms. So these are just the raw. These are the unstandardized coefficients that may be impacted by the metric. And then you get canonical loadings for set 1. Contains correlation coefficients between variables in set 1 and scores for set 1. And you can kind of, again, see that pre-test on forms for set 1, canonical loads for set 2, pre-test on forms, post-test on letters, pre-test on letters, post-test on forms. Pretty much confirm the standardized coefficients. So here, everybody, you just find a way of maybe reducing the dimensionality of 2 sets of variables. With 2 each, it's pretty simple. When you get more, it takes a little bit. Then you get this thing called redundancy analysis, which is the proportion of variance explained by each canonical variable. So do you see that 0.748 right there, everybody? Does everybody see that 0.748? Well, look if I took 0.817. Do you see that 0.817 right there for the canonical loadings? And 0.911 right there? If I add them up, divide by 2, 0.748. That's all it is. It's just taking the square root of those canonical loadings. And we can see there's a lot stronger one for the first one, the first variant. So, here everybody, I just want to give you an idea. I'm not going to get knee deep in canonical correlation, but if you ever have a project where you have two sets of variables and you want to reduce the dimensionality, it might be very helpful. It might be very helpful for you to consider using canonical correlation. And let's just, for fun, let's compare to multivariate regression, which is very, very similar. So let's go ahead, have pre-test on letters and post-test on letters predict the outcome. So you can get a multivariate test, everybody, and you have post-test on letters, and you have each of the predictors. And you will get some overlap in terms of the R-squares, but it's not going to reduce the dimensionality. It's a different type of research question. If you use two sets of predictors for multivariate regression, you're going to see how well they predict each of the outcomes, but you're not going to get it to reduce the dimensionality. And I just want to show you, in the old days, we used to do this using the Manova command. You can do, without invoking the macro, you can get parts of the output. If you do Manova, pretest with, does everybody see the with statement? Post-let, post-form, so it treats it kind of like a covariant, and then what you'll get, you will actually get the regression analysis, the R-squares, you'll get some of, you have to kind of look around at the output. There's the standardized and unstandardized coefficients. You have to kind of look around the output, everybody, but it'll give you some very similar results. If you want to use the Manova command for canonical correlation. So, let's practice with our in-class database. Exercise, diet, health, social influence, self-confidence, self-efficacy. So those are 6 scales we've been playing around with throughout the semester. Let's go ahead and see how well we can reduce dimensionality with demographics. Age. How many hours do you exercise? How many times a month do you eat fast food? What income level applies to you? We're pretending these are quantitative and continuous. So does everyone see we have 2 sets of predictors? One are our scale scores, and one is our demographics. And there's all the correlations for set 1 and for set 2, which you can get from SPSS. You're going to have 4 variants. Why? Because look, we have 6 variables there. The first one, 4 in there. So it's going to be the less. You're going to get as the maximum number of variants you're going to get will equal the less of the number of variables in one set. So here we see some pretty high ones, 0.5, 0.4, and smaller ones for the third and the fourth. And we have significance for the first ones, but not the third and the fourth. So there may not be that much to interpret for the last remaining ones. So let's just look, for now, let's just look at set 1, since that's got a good chunk of variance explained. Let's look at the biggest standardized coefficients. Exercise, diet, and nutrition. Does everybody see 0.49, 0.46? Demo 3 and Demo 2. So let's see what Demo 3 and Demo 2 was. How many hours do you exercise? How many times a month do you eat fast food? So fast food, hours exercise, kind of goes with exercise and diet. Does that seem to make sense? I mean, that's totally logical, isn't it? That's totally logical. So that's something that totally makes sense as a set of variables, that those seem to go together. Let's see if this, as you start going down, just like factor analysis, some of these may not make as much sense. But let's look at the second one. Exercise and diet are still the biggies. And here, same thing. But now we've got Demo 10. Now we've got Demo 10, which is income. So that may or may not be as interpretable. They're both significant. So now, everybody, I'm not going to go through the whole printout here, but what you see is I can go ahead and use canonical correlation. If you have 2 sets of variables, it may shed some really interesting insight into the relationship between 2 sets. So if you have job satisfaction, job commitment, professional commitment, job stress, job involvement, job engagement, let's say you have all these scales, and you have a bunch of variables such as tenure, salary, maybe some performance indices, right? I mean, that's another thing. Job attitudes and a bunch of performance measures. That would be a really cool use in IO psychology. Let's see, 6 or 7 measures of performance and 6 or 7 measures of job attitude. That could be a really nice use of canonical correlation. So that is that. Again, you won't have to run it for this class. Some people think multivariate books should get rid of canonical correlation, but I think it's still important to understand it and see it as a useful tool. That was used for years, and there's even an old article that was kind of a classic. It was kind of like called Canonical Correlation and the most, what did we call it? I think it was by Knapp back in the 70s. I have to find it. It was in Psych Bulletin. It was a really article by Knapp saying this was the most general linear model. Let's see if it even has that reference. That's it. God, it was by Knapp, 1978. Okay, I haven't looked at that article in decades. Canonical Correlation Analysis, a General Parametric Significance Testing System by T.R. Knapp, 1978, Psych Bulletin. Great article, you guys, great article. It's a little dated now, but yet Cohen's article about multiple regression as a general data analytic system, that was in 1968. Then in the 70s, you had Knapp, and then years later, Bruce Thompson. Bruce Thompson wrote about structured equation modeling being the most general linear model. And now if I wrote an article, which no one would ever ask me, we would extend this to called generalized linear models, the most general linear model. Generalized, which includes also dichotomous or count outcomes. So we've gone even beyond that. So everybody, that is canonical correlation. Any questions? So now let's move on to repeated measures. So I know you've already had a lot, but would it still be helpful to do a little, again, another primer on repeated measures?
Yes.
You guys all remember it perfectly from 6021 chat?
Been a few days.
Okay. Then we'll go ahead and...
Ross was telling me about it this weekend.
Was he?
It's really been a few days over.
I thought Ross was out of town.
He was on the phone.
Okay.
Assuming we were together.
Thank you. Chad, you know, you've just lied on tape. So, again, I'm not going to get knee-deep into a lot of the math, a little in the math, because we spent so much time on this already in 6021. But repeated measures is a multivariate design, and so far you have 2 or more potential outcomes, variables. And there's so many ways you can look at repeated measures. I think, and I've said this before, the advances in repeated measures designs have just been absolutely amazing in the last 10 years or so. I just got 2 books this past week. One called Longitudinal Structured Equation Modeling, another about intensive analysis.
When do you have time to read these books?
Oh, yesterday, I've got a new book on moderators and mediators, wonderful new book, very user-friendly. I'm going to recommend to students. I read a little chapter last night when I went to Betty Bye, and then...
before you go to bed?
Yeah, maybe for bed, and then during the week I'll do a little bit, and I always find time. Tonight I'll be giving a test at USD, and during the midterm, and I have my book in the cars. Actually, I have a book on item response theory, because I'll be lecturing on IRT to you guys. So I'm reviewing my IRT. So there's some wonderful books. I mean, there are, if you ever look at, let's see if I have it right here. I think I do. Hold on for a second, you guys. Have you guys seen the new Microsoft 8 operating system?
No, I don't want it.
My brother just got it this weekend.
I heard it was horrible.
Well, Scott, my brother's amazingly smart, so he's figuring stuff out on his own. It is not very intuitive.
Yeah.
I hope it scales like Vista, and then you don't have to worry about it. But
Doesn't it? Every time Microsoft launches something, isn't it initially an epic failure?
It's a good question. I don't know the answer to that, but it's...
Windows 7 wasn't bad, but they completely tried to change the interface just to make it more... I think they're trying to play catch up with Apple. It's trying to be too user friendly, like not user friendly, but visually appealing.
Yeah.
You know, trying to like change directions. But I heard it just, if you're a Windows user, it just completely just like tossed everything else out. Like there's not even a start menu or anything anymore.
Really?
So it's just, yeah.
I don't have this on me.
Everything I've read about them is that they just put like an interface on top of what they already have.
Yeah, it's a new shell on top of what they already have.
Yeah.
That's
Okay, my friends, repeated measures is when you want to look at change over time, right? It could be change, or you could also be exposed to multiple interventions over time. But the key thing is usually there's something done over time. The sometimes time could be a 2-hour study. And I would not call a 2-hour study. Let's say you're measured 3 times on a response task. I would not call that a longitudinal study. So make sure you use that word appropriately for longitudinal. Let's say we have 3 measures over time for quality of leader decision making. Okay, so just a basic self-report. You talk about the quality of your leader. And we're measuring him or her over 3 times with a very small sample size. Sample size of 5, and we see the mean 12.6 at time 1. Goes up the second week, goes down the third week, or month, or year, however you decide. Now, if this was done over 3 years, then you could probably call that a type of longitudinal design. And there may or may not have been an intervention. Sometimes you just measure things just to track the trajectory over time. Sometimes maybe there was a leader intervention. Maybe you sent them to Gene Greaves' company, Talent Smart, for emotional intelligence training. Now, you could do 3 paired t-tests, right? Time 1 versus 2, 2 versus 3, 1 versus 3, but what error is increased? Type 1, you got it. So this is a more powerful way, as we discussed extensively in 602.1 of doing analysis. Generally, you can get away with less people, and it also hopefully reduces error variance. And if we've reduced error variance, we've increased what? If we've reduced power, which means we've decreased yeah, that's right. We've decreased type 2. You got it. And there's lots of different designs that we're not going to get into this class, but there are so many designs you can do with repeated measures analysis. So, what you're going to find is there's 2 different approaches as we discussed. There's the univariate and multivariate approach. One that we'll focus on is the sum of squares or univariate approach. So we assume each test is orthogonal, which means you can pool together. You can pool together and get an average F test for 3 of these decision-making assessments. Since each individual serves in all conditions, you're able to take into account intra-individual variability. What does that term mean, everybody? Intra-individual. Yep, you're able to look at within. Exactly. Exactly. So here you have, just for 5 people, very small sample size, their scores over 3 time periods, and the individual mean. So we've always played around with the variable mean, as we did in Lenway and Nova, or even Manova. But now we're taking into account the individual mean. Right? And as you recall from 602.1, when you did it by hand, you actually extracted variance to capture the intra-individual variability. So here you have the means and standard deviations, and here's the bar charts for each of those. Now, I do want you to know that with some of the advances going on with using structure equation modeling for longitudinal studies, they are recommending try to get 4 or at least 5 measures over time. A lot of these more sophisticated statistics like more measures over time. If you have 3, though, you can still do the good old repeated measures. Your good old repeated measures. To get at the sum of squares, just showing you of the between. Take each mean from the grand mean, right? 12.6 is the mean for time 1 for leadership assessment. 15 is time 2. 13.8 is time 3. And that gets at between time or wave differences. Sometimes you'll see people will call it waves of data collection. So the mean square of the between is the degrees of freedom, number of time periods minus 1. So if we have 3 time periods, 3 minus 1 gives me degrees of freedom of 2, right? And there's your mean square, everybody, 7.2. So what does that mean square capture? That mean square captures the between time variability. And this is all tracked in your book on pages 417 and all the mathematics, if you want to follow. The sum of squares of B1, and this is where it deviates a little from how you did the math in 6021, but it's still going to give you the same answers. This gets at individual differences. Do you see that 13.67 right there, everybody? Where did I get that from?
Individual mean.
What's that?
Individual mean.
Does everybody see person number one? Right? So there's Stacy. She assessed her leader on 3 dimensions, and her mean is 13.67. And do you see why it makes sense you can calculate a mean for the person? Because once they have 2 or more measures over time, I can get a mean. That's right. It's no longer just a constant, as it would be for true between group design. So now I'm just going to take each person from the grand mean. So that's getting at individual differences. So it's like you're blocking on individuals, right? Remember what a block variable is when you block on males or females. Well, here you can block on time. There's a lot of ways you can do what's called blocked designs. So you're taking the mean for each individual from the grand mean, 93.77. So that gets at to some degree, the intra-individual variability. And then sum of squares within. You're going to take each score from the respective time period. Do you see where I got the 12 from? From each time. And that you did do. You did do that in 6021. So you take each score from the time period. So this is kind of like calculating what in one-way Nova? Each score from the variable. It was kind of like calculating to some degree the within, right? The within group variability. Hence why it's called SSW. So take each individual score from within their time periods, 160. So now you've went ahead and you've got these basic sum of squares. Thank you, Justin. And now you're ready to calculate sum of squares or residual. So you have the sum of squares within, which would be what you would get from a one-way Nova. You'd be stuck. But look what you get to do, everybody. You get to subtract. You get to subtract the variability you got blocking on individuals. Do you see you get to reduce your sum of squares from 160, which is exactly what you would get from the within group variance in an ANOVA context. But look, do you see I get to subtract 93? Which means if I reduce error variance, am I happy or sad? Yeah, you get to reduce error variance by repeated measures. And the mean squared residual is the sum of squares residual divided by n minus 1, k minus 1. That's sample size minus 1 times number of measures over time. When all said and done, we have a mean square between of 72, and we have an F of 0.87, because you took the mean square of the between, which is between the waves of data collection, 3 time periods, divided by the mean square residual, 0.87. And there's your F, everybody. There's your F. And as you all recall, so you just go into Analyze by point and click, General Linear Model, repeated measures. Right? You just go ahead and put in something. Now, just so you know, if you just type in time, there's nothing wrong with that. You're just defining the factor. But if you already have a variable in the database, I think you know what I mean? Sometimes you have a variable called time. So just keep in mind, you may have to give it a different name for whatever makes logical sense. We have 3 measures over time. And as you know, you just put in, as we did, under options. As you recall, we were able to actually get some type of post box aside at homogeneity we're going to discuss, effect size, descriptive stats. It's not going to be a very exciting plot. We'll have time on horizontal axis. And let's see what we get. So as you recall, you get a multivariate and a univariate test. The multivariate has its own host of assumptions. Do you remember from 602.1 what one of the major assumptions was for the multivariate test? Does anyone remember? And now you know about it because you've actually done it for your homework. What was the first assumption you tested for your homework and for the take-home?
Independence.
What's that? We did do that. Right? This requires multivariate normality. Because the algebra behind the multivariate is a bunch of matrices. It basically it uses determinants. And the determinant means it's got a vector of the means. So multivariate normality is necessary. For the within subject, it treats each one as a random variable. Time 1, time 2, time 3. So it pulls together the variance. So it is a little bit different, everybody, and has different assumptions. Just so you know, if you have two measures over time, they'll be exactly the same. There will be no difference between the multivariate test and the univariate, the within subject. They'll be exactly the same. When you have three measures over time, that's when things can kind of get a little bit different. Look at the eta squared, everybody, 69%. Wow. 17% here for within. It can be really different. Here, the multivariate test. Can anyone tell me how you can figure out quickly where they got partial eta squared from? You should remember this from Manova.
What's lambda?
What's 1 minus 0.304? Right. So remember, Wilks lambda is the determinant of error over the determinant of total. So if you think about the complement of that, it would be 1 minus the determinant of error over the determinant of total, which equals good old partial eta. Here, though, this is a function of sum of squares of time over sum of squares of total. So 14 and 66, it's about 70-ish. 14 divided by 70-ish or so will be about 17.9%. So they are different types of effect sizes. The multivariate. With small sample sizes, I do want to warn you, sometimes people say, oh God, they're so radically different, which one should I use? When you have small sample sizes, we have a sample size of 5. That's when you'll see those most appreciable differences. Once you have larger sample size, it won't be that radically different. But here, everybody, look what we confirmed from our hand calculation, from our hands. Sum of squares, 14.4. Sum of squares, 14.4 for the between. Mean square, 7.2. Residual, 66.23. Voila, 66.23. So we got everything we just did by hand. The F was 0.87. The P is 0.455. Using alpha of 0.05 for those repeated measures on leadership decision quality. Reject or fail to reject the null that there's no change over time in the quality of leadership decision making. What's that?
Fail to reject.
Fail to reject. Done your training, did maybe a training on emotional intelligence. You measured them over 3 months, once per month. There was no significant change. However, what caution would you have, Zach, with this? You are correct. We failed to reject.
Small sample size.
Small sample size. Because you know what? That's not a bad effect size. 17.9. It ain't chopped liver. Right? It's not bad. But you have 5 people. So you just treat it as a what?
Pilot.
Yeah, and I wouldn't even do a multivariate analysis on 5 people. I wouldn't even do it.
If you got a effect size that big that was not significant, such a small sample size, would it generally indicate to you that there was something there?
This could indicate one of two things. You're absolutely right. You could say, wow, we'll treat it as a pilot study, and gee, this is kind of an interesting forerunner of a more major study. Or it could be totally luck of the draw. Absolutely could be due to chance. You got 5 people. There's a chance that you just got some stronger or weaker managers, better leaders in decision making, more Yeah.
13?
It's a handout. It's called Chapter 13, Repeated Measure Notes.
It's in the notes.
I know you hate walking in the snowstorms, but I've been showing you the Manova syntax a lot this semester. And that's because there's some things the Manova does that the GLM doesn't. There are some things the Manova does. There is still a little more flexibility with the Manova that you can't quite do with the GLM. Such as, remember the assumption of that wonderful one that you have memorized now called homogeneous regression hyperplanes? When did we test that, Chad? For homogeneous regression hyperplanes. I'll give you multiple choice.
Godzilla.
Or when you have 3 or more covariates.
3 or more covariates.
Excellent, excellent. I haven't figured out how to do it in GLM. I know there's got to be a way to do it, and I have tried. I just can't figure out the code. But in Manova, it was pretty easy to figure out how to test that assumption. So Manova does have some flexibility that I found beyond GLM. But here I just want to show you, in the old days when we used to run Manova, which I did for my dissertation many years ago, there's your f of 0.87. There's your 2 sum of squares. There it is. So you get the same printout, but different. It's not as pretty. Then you can do, if the omnibus test is significant, if it is, then you can do what's called trend analysis to see if there's changes across time. See if there's any non-linearities. Right? So what if you have something? Unfortunately, it's going to be a weird video because we don't have a person here videoing it, which means they're definitely not tracking me. So, Ross, come here, please. I had you guys do this again. Now I want your opinion, Ross.
Literally come here?
Literally. No, metaphorically.
Right here.
Okay. IQ can't be that. Or can, but.
But does that say ass? I mean, what is that?
It says age.
Oh.
A-G-E.
Okay.
On camera. See that camera.
It is a type of donkey. Oh, look at that. That definitely says age.
Okay, so I don't get paid enough for this. Okay. Here's IQ. Draw what you think happens with IQ over time. Let's start at age 10. Dude, this will be a longitudinal approach unless you could do an intervention such as Head Start or something, but let's assume no intervention for now.
And then death at 60.
Okay, explain your theoretical change over time. And he did do a trend.
This may be more like a increases as you acquire knowledge in your formative years, levels off, and then maybe tapers in your older age as you become.
Levels off at about what age?
Probably closer to like here.
Okay.
30.
And it starts tapering off at about what age?
I'd say 70.
70.
This is as accurate as...
He knows his grade hasn't been submitted yet. He's played. He knows political savvy. Why do you think it tapers off?
I think that the neuron connections in your brain start to depress. The bio aspects.
General cognitive decline.
Yes.
General cognitive decline. Thank you. Very excellent. Well done. Well done. And yeah, they actually do find. There's some research that you guys know the difference of fluid and crystallized intelligence.
Yeah.
Fluid is almost like what you got, right? Crystallized is what you learn. Fluid does go down a little bit, and guess what the peak is? Some research says. Guess what age? 26. Say about 26. And then, but crystallized can continue, right? They talk about keeping your mind active, whether it be crossword puzzles. I read an article the other day, though. You know what's equally important to keeping cognitively engaged when you're older? Exercise.
Yeah.
They actually found
it keeps the oxygen there.
Yeah. Exercise is just as important with
Well, and
older.
we're not in really a culture that prizes old age, but there's some cultures where if you're older, you're the wise old person and you're
It's
revered.
very different in Taiwan. I know some from Taiwan. The way they treat the elderly is very different than that.
Moving.
Very, very different. So here, Ross, is this a perfectly linear trajectory over time? This is actually an interesting curve. There's these different types of curves out there. I'm not sure if this is it exactly. There's a thing called the Gompertz curve. And there's actually different types of curves. That would be more in different type of books. That actually, because there's kind of an exponential aspect to this, isn't there? There's kind of an exponential, maybe using the base for this part, they're leveling off. So there's actually all these different, I found one article a few years ago that showed all these different types of curves that you can actually model, using this as part of it. And so, that being said, you can do a trend analysis. Obviously, if you have 3 measures over time, maximally it'd be quadratic. What does quadratic look like? You can have concave down or a concave up, right? Absolutely. Now, some people have asked, what if I don't have significance for the omnibus test, but one of my nonlinear trends are significant? And that could happen, everybody. It's not implausible, but the quadratic might have had a p-value of 0.048, and your omnibus analysis was 0.063. You know, and I think you know me enough now that I'm pretty conservative when it comes to significance testing. So I still think you could interpret it if we got something like this that was significant. It might be interesting, but I still would be cautious if the overall analysis is not significant. And SSB1, which you found is 93.73, gets at individual differences. And this is in a separate table called the between subject effects. How can I tell it's between? Look at the error, 4 degrees of freedom, and this is the intercept. So this gives how each individual, so to speak, in the grand mean. This is usually going to be significant because it means how much do the scores differ from 0? Hopefully IQ differs from 0, a lot. So a lot of times this may not be that interpretable, the between subject effect. Is that quadratic? Yeah. So if I had a big sample size, guess what? It would have been significant. But we only had 5 people. So they're quality of leader, kind of low. They do an intervention. They go to Talent Smart. They learn about emotional intelligence. Wow, it goes up. Then no more training. Tell me what's going on that 3rd month.
Kind of reverting back to their old ways, but they're still not at, say, like something stuck. Something
Why would they revert back to their old ways if this was real data? What would be your kind of a post hoc theorizing?
Well, I mean, as far as just from the training I've had before, I know that sometimes a training can be almost motivational, and it'll really get you pumped to do something. But then, when you sort of get back into the atmosphere that you're working in, you kind of just fall back in your old ways, because when you do a training for the person, you're not necessarily changing their environment. Okay. So that the environmental cues that are there that kind of cause that behavior to begin with are still there, and so unless you change those in conjunction with training, you're probably going to
maybe go revert back.
Yeah.
Absolutely. You know, you find some of this, but it's U-shaped with weight loss programs. People maybe do a baseline measure of weight. They go to some of these programs, and they do a really nice job, and guess what happens when you look about a year later? In fact, why would some people gain more weight? Let's say someone's lost 40 or 50 pounds, and sometimes they do a year back, and even some people gain more weight. Why would there be that inverted U for weight loss programs?
The change in, not necessarily metabolism, but the way their body processes the food now that they may be eating at the same level they were, but their body's gone through a starvation phase, so it starts to store more fat.
Okay. That's good theory. What are these called? Where do they capture? And technically, each one is a confidence interval, right? So each one is a confidence interval, and this shows the means. Does one time seem to have more, as you said, variability or margin of error than the other? Yeah, the second time, right? And if you really want the line, you guys like that one or not? If you really want the combination of confidence interval and a line, do you like it or not really? Would you use this for a report or for your client?
No.
No? How come? Why would you not use it?
It doesn't make it more interpretal.
Okay, it doesn't make...
Maybe the two next to each other, but on the same graph seems too much going on.
Okay, so you don't think that would be... And again, that's an important part of graphics, is being able to something that resonates so immediately for the client, they don't need to beseech your advice to make sense of it. So it might be a little confusing. It might be. Now, one other option, everybody. Let me do graphs. And let me get what you think about this. Separate variables, simple. Let's go and do this. And then under options.
Didn't change.
What do you guys think of that one?
I don't like it.
Tell me
It's
why.
okay.
Do you see it's the bar chart and the confidence interval?
I think if you're working with somebody who isn't familiar with interpreting these types of charts, then this one would be more helpful than just the confidence interval chart. But it's still, for anybody that knows what they're looking at, it's just more than they need to be able to interpret.
Okay, so you find it more than you need, you were saying, Zach?
I just don't like it.
Because you'll see a lot of medical journals will have error bars. We just co-authored a paper we've submitted, and they absolutely required an error bar. And there's different types of error bars. This is the 95% confidence interval. You can also, if you're so inclined, everybody, you can also do it around the standard error. Doesn't look too different, does it? This is the standard error. See, plus or minus 2 standard errors. Or there's one more option. You can do it around standard deviation. Yeah, you guys don't seem overwhelmed, but just so you know, some of them,
I
especially...
just did that for my poster presentation.
You what?
I did that.
You did do.
Graphic for my poster presentation.
And did you feel that it helped illuminate the findings or between group differences and simultaneously not only gave you information about measures of location but also dispersion?
I did, that's why I picked it.
Yeah, because APA did have a recent article that says, the more we can use graphics that show both location and dispersion.
Yeah.
But I think you're right. Some people, I think, would agree with Zach that maybe they
Zach gave it
would be too busy.
It makes sense for a poster where you're kind of limited on space, but if I was trying to help someone interpret it, that if that wasn't an issue, I initially wouldn't.
But Chad's argument was that if someone understood standard errors or understood confidence intervals, right, they had a fundamental understanding, then you might find that a better graphic to show through repeated measures.
Well, no, the other one that didn't have bars, I think if someone was familiar with it, but like a poster presentation, somebody walking past, this would be quick and easy for them to see and interpret.
But I think you guys were talking about like a client, somebody that you had.
If you were going
like a
to
layman.
sit down with somebody and go through some information, it's...
Right. So I'm always thinking of graphics that can illuminate. The multivariate approach. So you've done the univariate, which is what you did by hand for 602A. Right? Considers measurement of subjects to be a sample from a multivariate normal distribution. And now you all know how to do the multivariate normal macro. Again, you guys, did you get any error messages at all when you were running the macro? Because there is temp files. The temp file has changed. I know that recently, you know what a temp file is when you have your computer? You've always had C:temp. And there's a lot of that in macros because they temporarily store files. I've noticed for newer operating systems, the temp file may be in a separate, different type of directory. So I've had to redirect some of the names of directories in the macros. So you may find some of these older macros, if they don't work, you may be doing everything perfectly, but it's just because of the location of the temp file. So I just want to give you a little warning. I just hit that with one of the macros. I had to rename all the file directories because I don't have a temp. It is. It's in another temp. It's under Dale/users/ something, right? Something completely different. So here, as we recall, it makes no assumptions about characteristics of the variance-covariance matrix, about multivariate. It doesn't talk about things like sphericity. The univariate approach requires assumptions about the variance-covariance matrix. The univariate has tended to be more powerful than multivariate for small sample sizes, some of the research. So that being said, everybody, think about this one approach. And this will help get at the univariate approach. Do you see time 1 minus time 2? 12 minus 14 is minus 2. Time 2 minus time 3. And then I would also have time 1 minus time 3. So there you can get a standard deviation for the difference scores, which is exactly what we did in 6021, when you can consider the assumption of sphericity, which we'll get into in a few minutes. So now, looking at the multivariate approach, you have time 1 minus time 2, time 2 minus time 3, and I can get a variance-covariance matrix of the difference scores. And look, everybody, there's the covariance, negative 7.15, and there's the variance of the difference scores, time 1 minus time 2, time minus 3. And then you can compute, as you know from chapter 2, the determinant. Right, this is all, notice this is all the multivariate approach. As you recall, the determinant, when you have a 2 by 2, right? When you have a 2 by 2, everybody, right? You just take this minus that one. But once you get the determinant, then for inversion, you've got to use that determinant and divide it by each of the elements. So this is all what we got from chapter 2. And that, everybody, ultimately helps get at standard deviation, SD1. And you can see this is a multivariate approach. Insofar, we're taking a linear combination of the outcomes. The univariate, you did the sum of squares for each one, right? Because each one is a random variable. So here, I do go into all the math for this that you may or may not be interested in. You can look at it maybe tonight when you go to bed, have a cup of Java, and then look through the mathematics. Chat, that may help with back pain or exacerbate. So here, basically, you can take what's called a mean vector, the mean of the difference scores, the variance-covariance matrix that was inverted, by the column vector. It all comes down to stuff we learned in chapter 2. It's all matrix algebra. A vector of means, a variance-covariance matrix of the difference scores, a column vector of means, 6.26. And we don't stop there. There's your t-square. Remember, t-square is the multivariate extension of what? The t-square is the multivariate extension of the t. Yeah. Right, the univariate t. Good old t-test.
I thought t squared was f.
Yeah.
T-square here, though, in this context, yes. In this context, you can do an F transformation of t squared. This is Hotelling's t. You're absolutely right. You do an F transformation, and there's the little formula.
There it is.
Sample size minus number of repeated measures, et cetera, et cetera. There's Hotelling t. This is just some rounding error, everybody, because I did it kind of by hand, 2.34. There's your 2.29. And then it becomes an F transformed to 3.4. And there's your multivariate test. So you see, it's kind of different than univariate. Univariate's a bunch of sum of squares. Here it really gets knee-deep into the matrix algebra. And what does it assume? Multivariate what? This assumes multivariate normality. And with small n, you may find rather different conclusions for univariate versus multivariate. You may find different p-values, different effect sizes. One may be significant, but the other one may not. I see this more when I have small sample sizes. So you do have to make a decision, you guys, before you start your analysis. Which one are you going to use for interpretation? Are you going to use the univariate or multivariate and come up with a justification for such? I usually use the univariate. It tends to be maybe a little more conservative. And then, as you know, we have some assumptions that I can make it as conservative as I need be. So that being said, everybody, you You guys all remember briefly, I discussed circularity. Remember that good old discussion we had on 6021? It requires that the sum of any two treatment variances minus their covariance equals a constant. And that's true for all pairs of treatments. See, to get at variance, everybody, how do you get at variance of a composite of variables? Have you gone over this in psychometrics? How to go over variance of a composite? Does that strike a bell for you in psychometrics? That's usually a real classic thing, usually in the statistical chapter in psychometric books. But it's the sum of the variances. Sum of the variances. So you have variance of item 1, item 2, plus item 3 for depression inventory. Right? Plus 2 times the covariance of x comma y. That's how you get at the variance of a composite. So if I have 3 items, I add up the variances and add the covariances. Here's the variance of the difference of variables. So here, everybody, there's ways of being able to get variance for a composite, which is used a lot in psychometrics. Circularity is kind of like that. And it means that we hope that the pairs of treatments all have similar variances. Compound symmetry has the property that both variances and covariances are constant. And you had that in your class. That was a test question. You had that on your exam, everybody, for your second exam. Because you kind of hoped, if this is the variances for 3 repeated measures, these are the, everybody remember the variances are on the diagonal? What's on the off diagonal?
Covariance.
Yes. Right? You hope the covariances are kind of similar, and you hope the variances are similar, which is the assumption having to do with compound symmetry. A matrix. Now, do not confuse. It doesn't mean the variances equals the covariances. In fact, that would be a huge problem. Do you know why? What's the determinant?
0.
Can you invert? Can you divide by 0, Zach? Which means you're going to have what? A type of error message. Will any statistical program spit out? If you cannot divide by the determinant, you can't use inversion because it's 0. What error message will it tell you? Dracula or singularity?
Singularity.
Singularity. You got it, right? That'll be singularity, exactly. So then, you have this matrix of the variances, covariance, and then each matrix is orthonormalized. What does orthonormal
What did you
mean?
just say?
Orthonormalized.
Orthonormal.
You make up words like hyperplane.
Oh no, no, I do not make up words.
Dracula.
No. In fact, you ever read Bram Stoker's book?
Yes.
It's a wonderful book. It's a love story in a
There's
weird
no
way.
statistics whatsoever.
Right? No, none. A matrix is orthonormal. I didn't make it up. If rows are both orthogonal and normal, hence orthonormal. So if I put that noun into an adjective.
Yeah, well, I make up words all the time. So
I know, but I'm not making it up though. Orthonormal, a vector is normalized by dividing each entry by the norm. Unit length is 1, right? You may remember from good old, in fact, I think sometimes they do things like this, like for a matrix like U, and I think that means unit length, which helps make things orthogonal. And here you can see that -1, 0, 1. Let's have those be the coefficients. And if I go ahead and take, right, when you have kind of the double lines like this, -1 plus 0 squared plus 1 squared divided by the square root is square root of 2. What do we do then, everybody? You have an orthonormalized vector. A normalized vector. Words I have not made up, Jocelyn. So I take that -1 divided by square root of 2. The square root of 2 is approximately 1.414, non-terminating decimal. 0 divided by that, 1 divided by the square root of 2. And it all equals 1. Isn't that cool? It's a little thing. So that makes it orthonormalized. That's what it does. By having basically all these repeated measures add up to this 1. And look, to see that I didn't make it up, smarty pants, Look what the old Manova says, orthonormalized.
You could
Yeah, you're
email
right.
somebody and say, how about this word? Let's put it in.
Yeah, you're right. You're right. You're right. Just like I could have made up the word called transposed, right?
No. I don't
Okay.
know that word.
Okay, yeah. So no, this came straight from SPSS, and you get for each one of these orthonormalized vectors, because I kind of guarantee you, as you will soon see, what if I square each of these? 0.57 squared plus 0.57 squared plus 0.57. Guess what that's going to equal? 0.707 squared plus 0.70 squared. So what's going to help everybody? Contrasts are normalized by dividing each contrast by the square root of the sum of squared loadings, coefficients. That brings us to sphericity. I didn't show you this as much. I didn't go into this detail in 602.1, but this is the black box behind sphericity. And under sphericity, you did get the word orthonormalized, and I will show you that again.
I investigated sphericity about a month ago. I don't remember why we were talking about it, but it was real hard to nail down. Everybody kind of had a different way of approaching explaining it, so it was real hard for me to...
The notion of sphericity. The notion of sphericity is that I have this matrix of difference scores. I have this matrix of time 1 minus time 2, time 2 minus time 3. Can I get a variance of the difference score? Can I get a variance?
Yeah.
And can I get a covariance of different scores?
Yeah.
Absolutely. So that kind of helps to some degree get at, in terms of the raw metric compound symmetry. Sphericity, as you just saw, orthonormalizes them. Makes each of these vectors for each time period uncorrelated, so to speak. When it multiplies, or takes into account its unit length, and it compares to this matrix, which is called the what? What matrix is this called, everybody?
Identity.
The identity matrix. One, see, when you orthonormalize a variable, it has a variance of 1, which means, guess what? It's a standardized variable. This means what type of covariance? Don't be shy. This means the covariance of different scores is 0. Excellent. 0. And that's what sphericity tests. The matrix is orthonormalized, and you have evidence that it's an identity matrix. 1 on the diagonal, 0's on the off, if you don't have significance. It means that you've got similar variances that are orthonormalized, but the covariances are 0, which means it kind of gets at a statistical test of independence to some degree. So the Mauchly test, the hypothesis that variance matrix of transform variables has constant variance in diagonal, 0's on the off. And there's your wonderful Mauchly's test of sphericity, which you all learned to love.
Yeah.
In 602.1. And look right here. You think I typed this in, orthonormalized? No, I didn't type in. Look at this. Now you really see, now that now you've learned a little bit about matrix algebra, this would have been a little confusing in 602.1. Test the null that the error covariance matrix of the orthonormalized transform DVs is proportional to an identity matrix. Now you know, there's your identity matrix. You saw how I went orthonormalized by this unit length, and you saw how we're able to test it. And there's your P of 0.19. Happy or sad? Do we want it to be significant? No. There you go. There you go. And that's kind of the black box behind sphericity. If it is significant, everybody, as you learned from 602.1, and you're using the univariate approach, then you will go ahead and use any of these 3 other options. I tend to use Greenhouse Geyser. It's probably because I'm most familiar with it, and it seems to have the best properties. Greenhouse Geyser, the only difference is it multiplies the degrees of freedom, right? It multiplies the degrees of freedom by the Greenhouse Geyser value, 0.599. If it gets closer to 1.0, I guarantee your p-value is closer to 0.9. Because it means it doesn't depart that much from the identity matrix. So here, if I took 0.59 to multiply by 2, there's your degrees of freedom. Which means you got a new critical F value, which will be what? More or less conservative. Its sphericity is not tenable? Will it be more or less conservative? The F value, the critical F value.
Less.
More. More conservative, right?
Why?
Because sometimes there's evidence that shows that when sphericity is violated, you have type 1 error, increase in type 1 error, which is false positives. So one way of kind of try to delimiting that increase in error is by just having different degrees of freedom, which makes it a little more stringent, hence a higher F critical value. So if sphericity was totally met, then epsilon, greenhouse Geyser, would be 1.0. There is also a thing called Heinfeld, everybody. The Heinfeld right there. Basically, here we see right here, Heinfeld is 0.712. It's just 1 times k minus 1. I'm sorry. No, that's for lower bound epsilon. Heinfeld is a slightly different formula that uses greenhouse Geyser. And here's for Manova, everybody. Here's what you get in Manova. There's my test of sphericity, P of 0.19, greenhouse Geyser. So now you can see you get a lot of this in Manova. I also show in the notes, so I'm not going to get knee deep into it. It's not a bad idea to look at confidence intervals. I show how to get at all these coefficients. The 23.9 that you get right there is the coefficient for an estimate for time 1. I show exactly how you can get at the confidence intervals, the t-values, test of significance, and how they even use these normed weights right there. But you really don't have to worry about that much. But just, I wanted to show you, all this is in the notes if you want to play around with it, to see how they got all these coefficients for each time period. And I just show you the math right there with each of the orthonormalized variants. So now we see we don't have significance, but let's pretend we do. Sphericity assumption looks good. Now, you could do some post hoc. There is no post hoc option point and click. As you recall from 6021, if you went into SPSS, everybody, analyze, general linear model, repeated measures, hit post hoc, blank, right? Got to have a between subject factor. But I did show you one thing you could be a little conservative is you can go to options, hit time, compare main effects, and hit the SIDAC, which is going to be kind of conservative. The book does show you can use the Tukey. Stephen's book does show using the good old Tukey, which, do you guys all remember the good old Tukey for pairwise comparisons? You have a student times range statistic. You have 3 means, so the student times range is 4.04. And then you just multiply it, the square root of the mean square of the error, which is 8.28, divided by sample size, 5.19. That means, everybody, that if any of the pair of means are greater than 5.19, you got significance. Time 1 minus time 2, 12 minus 6, minus 15 is minus 3.4. Nope. 15 minus 13.8 is 1.2. Nope. None of these. None of these are significant for the Tukey. But you'd have to do that by hand. If you wanted to use the Tukey for repeated measures, you'd have to do it by hand. There are some people that have said it's inappropriate to use some of these. They say those are geared for between subject, not within subject factors, and they're not quite taking into account the covariance of the measures. So there are some authors that recommend against using this, but Stephen doesn't seem to have a big problem with it. However, as I've recommended to you, is maybe using the SIDAC, which is definitely more conservative. More conservative, and we can see none of them are significant. There's time 1 versus 2, not significant. 1 versus 3, not significant, and 2 versus 3. So it is more conservative. So if you use the multivariate approach, you've got to address multivariate normality. If you use the univariate, you're going to address sphericity. We've already discussed to some degree trend analysis, looking at polynomials, linear and quadratic. What if this was stress over time? What would you say? You got 4 measures over time. Let's say it's someone interpret the higher the score, the higher the stress. This is month 1, month 2, month 3, month 4. And let's say a layoff happens right there.
was going to say there was a vacation somewhere.
Okay. What's going on? Let's pretend there was a layoff right about here.
Well, at first when you're laid off.
No, let's just say this is just regular. Stress is a little high. The stress goes a little bit down right at the layoff. What's going on at the month 3? Stress is what?
It's high again.
And then why has it gone down at 4 months?
All the layoffs are done.
What's that?
All the layoffs are done.
The layoffs are done.
Settling a little bit.
So maybe settling down a little bit. There's always a little bit of survivor guilt, right? That could be that. But here you got stress over time. Does it look perfectly linear? No. In fact, it's almost what? Yes. Which would be what type of polynomial, Chad? Raised to the power of?
3.
You got it. You got it. So it looks something like this. X plus x squared plus x3, right? To capture those 2 bends and curves for a cubic. Now, what about power for repeated measures? The book does give, actually, I have used this table for years. For page 430, it's a great table based on another article. Power is a thorny issue for repeated measures. You really have to know a lot of information. You have to have an idea about the means over time. If you have 2 groups, the standard deviations, it's not easy. Power and precision, the classic program doesn't even have an option for repeated measures designs. It has paired t-tests, and that's it. Because you have to understand also the covariance and the correlations. So here, for instance, if we go to page 430, let's say you have an alpha of 0.05. You have an alpha of 0.05 on page 430. And let's say you think the average correlation of your repeated measures. Your average correlation is about 0.5. It's about 0.5. And that, you'd have to know that from prior research. And then you can have a small, medium, or large effect size. So let's say we have a medium of 0.35, which is basically the F. A medium of 0.35, and you have 4 repeated measures. Look, you only need 27 people. Right? Small sample size, you only need 27. And what you should notice, if the autocorrelation is even higher, 0.8, you only need 13 people. If you have really high. So the more that the repeated measures are correlated, you actually can get away with less people, showing the power, the increased power for repeated measures. Now, I do want to show you one cool option, and I did discuss power in depth our first lecture, but these articles are really worth availing yourself of for your dissertation or work site. If you ever do power analysis for multivariate repeated measures designs, this is a great way to use SPSS. And guess what? You got to use the Manova syntax. Got to use the Manova. And I've put all this syntax in here. Plus, I did put the power analysis presentation on Blackboard, and you can cut and paste the syntax. But let's say I've got 27 people, 4 repeated measures, average correlation of 0.5. Exactly what I just shared with you from the book. So here, I use this matrix language, patient satisfaction time 1, time 2, time 3, time 4, begin data. Here's the means that I think are going to happen. So you got to put in your best information. So let's say I think the means of patient sat will go up from 20 to 23 to 25, 27 on a self-report inventory. Then you got to have an idea of the standard deviations. You need an idea of the standard deviations. And here's the correlations. I think the average correlation will be 0.5. So that's all you have to put in. And then you do the Manova syntax. The Manova, patient satisfaction within subjects. And then you get this power line. This is the crucial one called power. And it's pretty cool, everybody. Here you can see you get a power of 0.99. This is a power of 0.99 for the multivariate test. But let's look at the inner. And here, for the within, you have a power of 0.997. So you have more than enough power. In fact, which gets me to think, this 27 in your book, right, oh, you know why? Because it's got a larger effect size. I bet the way I did the means, it's probably got a larger effect size than 0.35. Which means you could play around with this, everybody, and maybe get away with less people. You can maybe get away. So let me show you. Let's play around with this really quick, just for fun. Here we go. Just cut and paste. Control-C. Easy schmeezy. File. I'll let you on break in a few minutes. See, you guys can play around with this. You can take my notes or just cut and paste it into syntax. But let's go ahead and do less than 27. Let's try 20. Let's just run this whole thing. There we go. It's a pretty cool macro. It's pretty cool. Wow, power is 0.92. Well, let's try 10 people. Oops, power's 0.44. But listen, look, this is when things are weird, everybody. Look at the multivariate. 0.44 power for multivariate, not significant. Significant for univariate, 0.734. P is 0.025. Do you see the disconnect here sometimes with smaller sample sizes in the multi? That's a great example of a slight disconnect of multivariate and univariate. So there you can, this is a great way that you can start doing power analysis, everybody, for your dissertations. And that is definitely one, and you can do this in G-Power. G-Power, which is free. I just went ahead and ran this in G-Power. I put in effect size of 0.35 per the book, a sample size of 27 per the book, and I got more than enough power, 0.99. And I put an average correlation of repeated measures of 0.5. Which means I'm thinking that that book may have been a little conservative. And Manova approach indicates I get away with 16 people. I can get away with as low as 16. So there's ways that you can do this type of power analysis for between and within designs. And as you already know, if you're at all interested, everybody, if you're at all interested, and I did post this for your edification. Find PowerPoint, file, open. I believe I saved it for you. Yep. I put this for you right at the beginning of the semester. I've got all types of examples of how to use, using this book, Applied Power Analysis, and some of these articles by Osborne. I did all types of examples for ANOVA, ANCOVA, mixed ANOVA. So you'll see lots of examples in my presentation. You may want to avail yourself. Let's go ahead and take 15. We'll start at 10:53.
Us to take on next week.
Yeah, remind me next week. I'll be happy to post it for you.
What all is on it?
What is all on it? Lots of really good stuff.
I'm excited.
Only 3 little questions.
3 little guys.
EFA, Manova, and logistics/discriminant function analysis. I guess it's 4, but both those are embedded in one. So that'll be no repeated measures because you've had enough analysis on 2. So that'll be that. Okay, everybody be good.